Welcome to the deep dive, everyone. We're really glad you're here today. We're going to be exploring the fascinating world of human performance and, well, physiological adaptation.
Yeah, thanks for having me. It's a great topic.
And the mission for today's deep dive is actually really specific. We're looking at how micromanipulations in the duration of a sprint can, completely fundamentally alter your human physiology.
Right. It's all about how the body interprets time and tension.
Exactly. And how you can use that to hack your own adaptations. So, to guide us, we're looking at a really rigorous piece of scientific literature. It's titled Influence of Repeated Sprint Bout Duration in Sprint Interval Training Intervention on Physical Performance Adaptations of Young Volleyball Players.
Wait, a mouthful, yeah?
It is, yeah. It was authored by Zhang, Ma, and Li. And it was published in the Journal of Sports Science and Medicine in 2026.
And I have to say, it is a remarkable piece of literature. The methodology they use gives us this incredibly pristine look at, metabolic pathways.
So to get us started, I want you to imagine something. You head into the gym or out to the track to do a sprint workout, and you decide exactly how much total work you're going to do. Let's say, I don't know, exactly 3 minutes of all-out, maximal effort sprinting.
Right. A solid block of work.
Yeah. You don't change the distance, you don't change the total time under tension, and you keep the exact same ratio of work to rest. But just by slicing up that total time differently, like chopping those 3 minutes into slightly different fractions, you actually fundamentally alter your own physiological destiny.
It really is wild.
Slice it one way, and you walk out a highly explosive jumper. But slice it another way, and you become this highly agile runner capable of sustaining power under deep fatigue.
The premise feels almost counterintuitive, honestly. I mean, we are so conditioned to view athletic training as this basic ledger of volume. You either put in the work or you didn't.
Right, you ran the miles or you stayed on the couch.
Exactly. But this research demonstrates that the human body isn't just measuring total output. It's exquisitely sensitive to the specific cellular demands we place on it. It responds to the exact duration of the stressor.
Well, before we start dissecting the split-second math of these sprint intervals, we should probably establish why these researchers chose volleyball players. I mean, when you think of a track meet or a sprint clinic, volleyball doesn't exactly come to mind.
No, not at all.
It's a sport defined almost entirely by verticality, right? Jumping.
Yeah, but volleyball has this distinct temporal and mechanical profile that makes it the perfect laboratory for this specific question. A volleyball match is basically characterized by short, incredibly intense bursts of activity.
We're talking, what, a few seconds at a time?
Right, efforts lasting between 3 to 9 seconds. Think of the sudden, violent acceleration of an approach run for a spike, or
Right. A rapid lateral dive to dig a ball.
exactly, or a max effort block jump. And following that 3 to 9 second explosion, the athletes typically get about 10 to 20 seconds of, low-intensity recovery before the next serve or the next play.
And historically, to get better at those explosive upward movements, the traditional approach has always been plyometrics. Box jumps, depth jumps, bounding drills. Athletes just spend hours jumping to get better at jumping.
Which works. Plyometrics are undeniably effective for enhancing neuromuscular power, but the issue is the mechanical toll. Volleyball players are already jumping hundreds of times a week during standard practice.
Yeah, just from playing the game.
Right. So when you stack high volumes of plyometric training on top of that baseline, the cumulative mechanical load becomes hazardous. The sheer force of absorbing those repeated jump landings leads to a really steep increase in overuse injuries.
Like, what kind of injuries are we talking about?
You start seeing chronic patellofemoral pain, severe ankle sprains, and accelerated joint degradation.
Basically, the structural hardware of the knees and ankles just starts to wear down from the impact. Which brings us to the intervention the researchers were testing to solve this whole problem. The repeated sprint training, or RST. The concept here is to use high-intensity, short-duration sprints to build explosive power instead of jumping.
Yeah, exactly.
It's kind of like upgrading the electrical system in your car to deliver a massive spark without having to actually take the entire engine block out and rebuild it. You get the peak neural output without the structural wear and tear of a hard landing. But I do have to ask, does running in a straight line actually make you better at jumping vertically?
It does. And the mechanism connecting sprinting and jumping comes down to how your nervous system governs motor units. So a motor unit is essentially a single nerve fiber and the specific bundle of muscle fibers it commands.
Okay, got it.
When you sprint at an absolute maximal effort, your brain is forced to recruit a massive number of these motor units simultaneously.
So it's a synchronization challenge, like a rowing team. If everyone rows at slightly different times, the boat just kind of glides along. But if you demand the nervous system to make every single rower pull at the exact same millisecond,
The boat violently surges forward. That is a perfect way to visualize it. That synchronization is what we call rate coding and firing frequency. The neural software required to recruit all those motor units and accelerate your body weight forward at maximum velocity is practically identical to the neural software required to propel your body upward against gravity.
wow, really? It's the same software.
Yeah. By doing repeated sprint training, the athletes build the capacity for instantaneous force generation. They train the nervous system to fire a massive synchronized signal without subjecting their joints to the mechanical trauma of landing.
Okay, so knowing that RST is a viable joint-saving tool, let's look at the actual experiment here, because the control variables are what make this study so compelling. The researchers recruited 40 young male amateur volleyball players, all around 19 years old, and split them into 4 groups. One was a control group. They just continued standard practice. And the remaining 3 groups underwent a 6-week RST intervention, completing 18 training sessions in total.
And the elegance of the design lies in the total workload. The total bout duration for all 3 intervention groups was completely identical.
They all did the exact same amount of work.
Yes. Every athlete in the experimental groups sprinted for exactly 180 seconds per session. Furthermore, they all operated on a strict 1.3 work-to-rest ratio. The sole variable manipulated in the study was how those 180 seconds of sprinting were distributed.
Okay, let's break down the math on those distributions. Group 1 performed 3-second sprints. So to accumulate 180 seconds of total work, that group had to perform 60 individual repetitions, which they broke down into 2 sets of 30 reps, sprinting about 25 meters each time.
Okay.
Group 2 performed 6-second sprints. That meant 30 repetitions, sprinting roughly 45 meters per rep. And Group 3 performed 9-second sprints, doing 20 repetitions of 75 meters.
Right, so the same total time sprinting, same exact ratio of rest to work.
Yeah, exactly. But if my body is subjected to 180 total seconds of maximal output, I mean, I'd assume the metabolic tax is the same. Why would my cells care if the math is chopped into 60 tiny pieces or 20 larger pieces?
Oh, your cells care deeply. Because the human body does not run on a single uniform energy system. It relies on overlapping energy pathways that are highly sensitive to time.
Okay, so how does that work in a 3-second sprint?
During a 3-second sprint, your muscles are primarily drawing on the ATP-PCR system, which is often called the phosphagen system. This system uses stored adenosine triphosphate and phosphocreatine to generate a massive amount of energy almost instantaneously.
It's like having cash in your pocket. You can spend it immediately without any processing delay, but you only have a few dollars. It runs out incredibly fast.
Exactly. And once that immediate cellular cash is gone, the body has to switch to a different payment method to keep the muscles contracting.
Which is what?
Well, in a 3-second window, the body barely dips into the glycolytic system. Glycolysis is the pathway that breaks down carbohydrates to sustain intense effort, but it comes with a cost.
The burn, right?
Yeah, the rapid accumulation of metabolic byproducts like hydrogen ions. That causes that burning sensation and ultimately interferes with muscle contraction. So, as you stretch a sprint past the 6-second mark and push toward 9 seconds, you exhaust the immediate phosphagen cache and force the body to rely heavily on glycolysis.
So even though the total seconds of the workout are identical across the groups, the actual environment inside the muscles is different.
Right. The metabolic environment inside a muscle cell at second 8 of a sprint is bathed in metabolic stress compared to the pristine environment at second 2.
So if the body's relying on completely different fuel sources depending on the second hand of the stopwatch, we should expect to see completely different physical adaptations by the end of the 6 weeks.
And that is exactly what the data showed.
Let's start with the group that performed the 60 tiny 3-second sprints. This group saw the most dramatic improvements in their counter-movement vertical jump, which is, that dynamic load and explode jump where you dip down before launching.
Yeah.
They also saw the best improvements in their 10-meter and 20-meter linear sprint times, their reactive strength index, and their peak power output.
And the reactive strength index, or RSI, is a phenomenal metric here. It's calculated by having an athlete step off a small box, land, and immediately rebound into a maximal vertical jump.
Oh, wow. So it measures how fast you can bounce back up.
Exactly. It measures jump height divided by ground contact time. It isolates the stretch shortening cycle, showing us exactly how fast the neuromuscular system can absorb downward force and explosively redirect it upward. And the 3-second group absolutely excelled in this.
See, this presents a fascinating paradox to me. The athletes in the 3-second group ran the absolute shortest distance. They only ever sprinted 25 meters at a time before stopping. Yet they were the ones who developed the highest vertical jumps and the fastest reactive explosiveness.
It does seem strange on the surface.
Yeah, I struggle to see how such a short, abbreviated run translates so powerfully to upward explosion.
The insight lies in looking past the distance and focusing on the mechanical initiations. Consider the structure here. To hit their 180 seconds, the 3-second group had to perform 60 separate repetitions. The 9-second group only performed 20.
Oh, I see. They had to accelerate from a dead stop 3 times as often. We shouldn't even call this sprint training for this group. We should probably call it acceleration training.
That is a much more accurate label, actually. Accelerating from a stationary position requires a monumental spike in horizontal force production. You're demanding the nervous system to jolt the muscles from 0 to absolute maximum capacity instantly.
Like flipping a switch.
Right, and by forcing the athletes to execute that dead stop acceleration 60 times per session, the researchers were hyperdosing the exact neural pathways responsible for explosive power. Furthermore, because the bouts only lasted 3 seconds, the athletes never accumulated that acidic glycolytic fatigue we discussed earlier.
So they stayed out of the pain cave.
Exactly. They relied on the clean-burning phosphagen system, recovered, and fired maximally again. They were practicing pure, unadulterated neural activation without metabolic interference blunting the signal.
So the 3-second protocol forged these highly explosive athletes. Does that mean the 9-second protocol was a failure? Because if a volleyball player needs explosiveness, it would seem like extending the sprint to 9 seconds is totally counterproductive.
Well, it wasn't a failure at all. It was simply a different evolutionary pressure, which yielded a different adaptation. The 9-second group didn't achieve the same massive spikes in vertical jump or pure acceleration. Instead, their superior adaptations manifested in the t-test change of direction speed and their mean power output.
And mean power was measured via a 30-second all-out Wingate cycling test, right?
Yes, exactly.
The t-test result is another brilliant paradox in this methodology because, just for the listener, the t-test is a brutal, multi-directional agility metric. You sprint forward, you shuffle laterally across the top of a tee, you shuffle all the way back across, and then you backpedal to the start.
It's exhausting.
Yeah, it demands constant deceleration and reacceleration in different planes of motion. Yet, the players in this study did their intervention by sprinting in a straight line down an indoor corridor for 75 meters. How in the world does straight line running for 9 seconds improve multi-directional lateral agility?
The adaptation comes from the internal physiological burden driven by the recovery ratio. We have to look at the work-to-rest dynamic. Every group utilized a 1.3 ratio. For the 3-second group, that meant 3 seconds of work followed by 9 seconds of rest.
Okay, so it keeps the heart rate up, but the durations are short.
Right. But for the 9-second group, a 1.3 ratio dictates 9 seconds of maximal sprinting followed by 27 seconds of recovery.
Ah, okay. That's a huge difference in rest time.
That 27-second window is transformative. It allows for a much more complete resynthesis of phosphocreatine in the muscle belly. However, because a 9-second maximal sprint heavily taxes the glycolytic system, subjecting the body to 20 repetitions of this builds an immense amount of metabolic stress over the session.
So the body has to adapt to that stress.
Exactly. The body is forced to adapt by upregulating both aerobic and anaerobic enzyme activity. It basically builds a larger, more robust biological engine capable of clearing waste and sustaining high-intensity contractions even as the environment inside the cell becomes highly acidic.
So, if I'm understanding this, the 3-second group built a massive engine to deliver an instantaneous spark. But the 9-second group built a superior cooling and filtration system. They trained their muscles to sustain a high power output without stalling, even when they were flooded with fatigue.
That's spot on.
And agility tests like the t-test are exhausting. Your form breaks down not because you lack the strength to shuffle, but because your muscles are just suffocating in metabolic byproducts.
You've hit on the exact mechanism there. Agility isn't just about one explosive step, it's about maintaining mechanical efficiency during a complex task under load. The 9-second group improved their lateral shuffling because their improved glycolytic capacity allowed them to clear fatigue and sustain power output over the entire duration of the test. The internal structure of the interval dictated the physiological upgrade, regardless of the fact that they were only running in straight lines.
That makes perfect sense. So we've thoroughly explored the extremes here. The pure neural spark of the 3-second bout and the glycolytic stamina of the 9-second bout. Let's spend some time on the 6-second group. Where do the athletes who trained right in the middle fall on this performance spectrum?
The 6-second group serves as a really fascinating study in hybrid adaptation. They exhibited moderate, statistically significant gains across the entire board.
A bit of everything then.
Yeah, they improved their vertical jump and 10-meter acceleration, though not to the heights of the 3-second group. Simultaneously, they improved their agility and mean power output, though not quite to the level of the 9-second group.
So they basically landed in a physiological Goldilocks zone.
Pretty much.
It wasn't just a compromise, it functioned as a balanced dual-threat stimulus.
Yeah.
At 6 seconds, the body is right at the precipice. You're maximizing the output of the phosphagen system while just beginning to trigger the initial stress response of the glycolytic system.
And that creates a unique tug-of-war in the muscle fibers. For sports that require a continuous transition between pure explosiveness and sustained high-intensity output. Think of like a soccer midfielder who has to accelerate to win a header, then immediately sprint 40 yards to join a counterattack. This 6-second domain is incredibly valuable.
I could see that.
It trains the nervous system to fire rapidly while simultaneously challenging the metabolic systems to start handling waste products. It builds a highly versatile, resilient athlete profile.
Well, this brings us to the most crucial part of our discussion: application. If you are listening to this and planning your own physical training, whether you're a competitive athlete, a weekend warrior, or just someone looking to optimize your time on the track, how do you leverage this science? What's the ultimate takeaway here?
The core lesson here is the power of targeted intent. Sprint training is not some monolithic activity that simply makes you fitter. You possess a highly precise dial duration that directly controls which athletic trait you upgrade.
So you really have to know what you want before you start the stopwatch.
Exactly. You have to analyze your specific performance goals. If your objective is raw, explosive acceleration, like if you want to maximize your vertical jump, react faster off a starting line, or generate peak power instantly, your programming should focus on ultra-short, highly repetitive bursts.
Keep the work under 3 or 4 seconds.
Yes. Execute a high volume of repetitions to force your nervous system to initiate movement from a dead stop repeatedly.
But if your performance goals require sustained output, say you play tennis and need to maintain lateral agility deep into the 3rd set, or you want to hold your top speed during the final stretch of a grueling trail run,
then your programming must shift. You need to push your intervals closer to the 9 or 10-second mark. You will require longer recovery periods to match the 1.3 ratio, but that extended duration is non-negotiable.
Right.
You have to purposefully submerge your muscle fibers in that glycolytic stress to force the enzymatic adaptations. You are actively training your physiology to keep functioning smoothly in a highly fatigued state.
This study is just a masterclass in the precision of human physiology. Manipulating bout duration isn't a matter of scheduling convenience. It is a highly calibrated tool for dictating exactly how your body rewires itself.
It really is.
For a comprehensive look at the statistical modeling, the specific effect sizes, and the rigorous testing parameters, I highly recommend reading the full article. Again, that is Influence of Repeated Sprint Bout Duration in Sprint Interval Training Intervention on Physical Performance Adaptations of Young Volleyball Players by Zhang, Ma, and Li, published in the Journal of Sports Science and Medicine.
The depth of data in their research beautifully illustrates just how responsive the human machine is to the precise mathematical instructions we feed it through physical training.
And to ensure you're always equipped with these kinds of actionable, scientifically rigorous insights, make sure you follow the channel and turn on your notifications so you never miss a deep dive like this.
And, I want to leave you with a final concept to consider before we go. We've spent this time discussing how shifting a physical effort from 3 seconds to 9 seconds entirely dictates whether your muscles adapt for upward explosion or sustained, fatigued agility.
Right.
It forces a broader question, I think. What other subtle durations in your daily life are quietly reshaping your capabilities without you even realizing it? Consider the exact length of the deep work focus blocks you schedule at your desk. Consider the duration of the micro breaks you take to scroll on your phone.
Oh, that's a really interesting point.
Your brain and body are not static. They are constantly adapting to the intervals you subject them to.
That's powerful. Are you slicing up your time in a way that builds an explosive, highly capable mind? Or are your daily intervals accidentally training you to sustain a state of perpetual fatigue? It all comes down to the math. Thanks for joining us, everyone. Until next time.